Right, so here's a quick setup on how to emulate analog video signals in TouchDesigner. We'll be getting our movie file in here, converting it to YIQ color space, doing some blurring, some noising, some more noising, and decoding it back to RGB, and maybe add some bloom here and outputting it. So it's a very simple node graph. We will be doing some GLSL though, but it's very simple and easy to follow along. So let me just show you what we'll be doing. Let me put down my brush size to 12. The basic setup is we have a RGB in. That's going to be our video. It can be live maybe. And we'll be converting it to YIQ. Why we do that, I'll explain in a second, but for now, Y is the luma, I stands for in phase, and Q stands for quadrature. And this is basically a color space slash model, color model. And after our decode, we will be doing some, or after our encode, we will be doing some effects like Chroma Bleeding. We can do noise channels or channel noises, frame stutters, and then we'll be decoding it back to RGB. So we have a output that we can use in our digital world, and this is basically the inverse of that. And this is where all our effects live in. So let's just get into our new TouchDesigner file here. Delete everything, close that, and just get in a movie file, not out, in. Let's use the jelly beans. And first things first, let's fit it down to a lower resolution, since that's what the NTSC standard wants from us. So 640 by 480, and we can do a fit outside here so we don't have the black bars top and bottom. And let's just drop in our first GLSL node here. Let's keep them here maybe. And what this basically does, if you're new to GLSL, this basically just dictates what each pixel should look like. So in our frac color down here, if I say, look, I want a RGBA value, so vector with 4 values of, I don't know, 0.3, 0.4, and 0.5, and an alpha of 1. That's the color we've got. So that's pretty much what we're doing here, and we can also get our input here. So if we uncomment this is our input, and if we say I just want the frac color to be color, we can also get that. So this is the very basics of GLSL. And instead of having color here, I want to convert the RGB to YIQ. So let's just grab the RGB values from our image. That is a VEC3. I'm sorry. So let's do RGB. And we can just grab this. I don't want to type that out. I just want the RGB channels of that. And let's get some floats. YIQ. And there we go. Just have our basic structure, and then our output. I want YIQ and an alpha of 1. And what this basically does is it stores the Y into the red channel, the I into the green channel, and the Q into the blue channel, which is going to look wrong in here, but we're just saving it since we can't rename the channels in here. Not that I know of, at least. And where the YIQ floats come from is back in the day, people had televisions, right? So the first TVs were black and white, and they had a signal that's just like a single channel, and that basically just says how bright should a pixel, or not a pixel, but how bright should a spot on the screen be. When color TVs came about, the scientists in the 50s, they were nice people, so they wanted to keep backwards compatibility with black and white TV, so that people who still had a black and white TV could still watch TV without upgrading to color TVs. I mean, that's probably the business model of today, to kind of force people to buy new TVs so they can continue watching. But back in the day, people were nicer to each other, so they retained backwards compatibility. And this is not possible with, let me draw an R here. That's not possible with RGB, since this splits out the colors. So if we have an image that's like flat in red, so 0 red, but a lot of green and blue, if we just took the R here, it's going to be a black image. So you can't really use this. You have to use a channel dedicated to luma, or brightness. So that's what they did. Then they figured out how to pack the color information into I and Q. So how this works is they put these two into a subcarrier like they did with the audio signal, and this lives in a certain frequency. So this stayed the same frequency, so the black and white TVs could still receive it and people could still watch it. And they put this into a frequency higher, so even if the black and white TVs got it, it would just kind of make the image a bit more fuzzy. It wouldn't get interpreted. So the higher frequency wouldn't get quote unquote seen by the black and white TVs. And this still had to be in a singular channel. So they just added all the signals together to make a very messy big signal. But since the black and white TVs only receive this, that is where the Y lived. The higher frequencies would be the I and Q. And how the color TV got it is basically through filtering. So if you've done any audio work, you know that there's bass, there's, what's the middle one called? There's middle, and then there's highs, right? And you can have an audio file, single channel, mono, and you can still hear like the cello, you can still hear the violins, you can still hear the people singing in the middle. And that's basically how the color TV separated the channels. So that's what we will be doing here. How they figured out what I and Q should be is through a smart little matrix here. I got this from Wikipedia. If we put down some colors here, I'm just gonna do a green one, a red one, and a blue one. And you kind of just squint your eyes, you can see that the green kind of looks the brightest, even though they're all, you know, on the top here. So what they figured out, people perceive the color green brighter than red or blue. Red is kind of like in the middle, it's there, it's neutral, and blue is kind of, it just kind of looks really dark, to be honest. And so that's what they did here. In our Y channel, how they figured out what Y should be is Y is, or the red is kind of like mid. It's not that bright. The green is really bright, so green things kind of just look brighter, and the blue is really dark. So we will be using these values to encode our Y, and how they figured out I and Q is just basically what is left of everything. And I, in this case, is a spectrum from orange to teal or blue, and Q is green to magenta. But yeah, we'll just use these values. And trust me, this is the hardest part of it all. Afterwards, it's just fun and games, but we just have to type these values in. Feel free to skip this. This is very boring, but we have to do it. So let me just grab our values. So 0.299 times RGB of the red plus 0.587 of the green plus 0.114 of the blue and minus 0.599 of the red, negative 0.2746 of the green, and negative 0.312 of the blue, oops, and 0.215 of the red, minus 0.527 of the green, and 312 of the blue. Alright, so we got an image that looks absolutely horrendous. Actually, it looks kind of nice, but yeah, so we are basically in YIQ color space here. Don't mind the representation here. Yeah, we got RGB, but this should be, in theory, YIQ. We're just storing the YIQ and the RGB values here. And also, let's change this to 32-bit float, since that is best practice. And we can drop in our decode here. Honestly, we're just doing the same thing as this, but let's just type in the values new because they're completely different. But yeah, let's go. So again, vector 3, let's call this YIQ, and let's grab the input, and I'm grabbing the RGB here. Since we're storing it in the RGB of this, it is the YIQ. But yeah, so get rid of that. I want this. I want to be R. Should I put it in capital? I don't know. Doesn't matter. And again, let's define R. Let's define G. And let's define B. And here we're going from YIQ to RGB. So let's do that. They will start with 1. That is nice. So we can just do RGB.R. I don't think I need to explain why we don't need to multiply that by 1. But yeah, next thing. Oh, by the way, this should not be RGB.R. It should be YIQ.R. Because this is that. And let's plus 0.96 of green, plus 0.619 of the blue. Let's do 0.272 of sorry, YIQ. Don't listen to me. I'm an idiot. Right. So minus 0.647 of YIQ.B, and minus 0.6 of green, space there, and 1.73 of YIQ blue. And we will have the exact same image. So don't worry, we didn't do this for nothing. All the pain was worth it, because we're now working in the beautiful YIQ color space. Yeah, I guess the first thing we can do is we can split out the YIQ into separate tops with the reorder. In the reorder, we stored the Y in the red channels. So let's just put green and blue to 0. And let's put down 2 more. We stored the I value in green, and we stored the Q value in blue. There we go. And after that, we can put down another reorder and just plug it all back in. Let's move this over. This is not looking that satisfying. And here, I'm just gonna merge them together again. So I want the red of input 1, the green of input 2, and the blue of input 3. Got the same image. Let's put down a null here. Let's call it digital out. Let's view this. And let's just check if everything is correct. So, oops. We got 32-bit float, right resolution. Okay, looks good. So let's just start blurring. So this is a effect of band limiting, of what people used to do back in the day. to save some space. So let's put down a blur here. And this is probably, my face is covering the jelly beans. Let's put down a blur here. And this is probably the, it's probably not the most significant effect, but it's a very important thing in things, I don't know. And you can already see that it's kind of giving these little halos around the color edges. Yeah, this is Chroma Bleeding basically, and we can add another blur here. And since the Q travels at a lower resolution because the people didn't deem it as important, because they figured that people would notice green and magenta differences as significantly as orange and teal contrasts. They just put in a lower resolution frequency range. So we can probably blur this a bit more than that. So let's do 12, maybe 10. You can already have some nice bleeding things here if we disable these. That's pretty nice. We can maybe even add some noise. Not maybe, we will be adding some noise. So let's put down an add node here. Add top. Also a noise. And let's just put it on and see what happens. You can see that it's in the magenta. And if we, by the way, just put down an add here and a noise here, you can see that it's going into orange. So you see, you know the setup is working. So let's just disable that for a second. And we can use simplex. Let's turn on the period so we get more, we got finer grain. Let's animate this with that little expression apps time, not seconds. And you can see that if we do a to chop here, oops, you can see it's going from 0 to 1, so it's adding positive values, but I want to sometimes maybe even subtract from values. So I'm going to turn the offset to 0, so it's going from 0 to 0.5, since we are still in 8-bit float here. That can't go negative, but as soon as we go 32-bit float, it can go to negative 0.5, and we see green grain as well. And let's turn down the amplitude, maybe 0.05 for some subtle grain or noise. We can put some noise here as well with the same expression. Oops, I cannot believe it. Let's just put down an offset so that both of the noises don't look exactly the same. A little less period, and this noise should be less because it is a better signal, so to say. So let's just also put offset to 0 and amplitude to maybe like 0.01. And we can also just put it on the entire signal. So let's put down an add here, a noise here. Let's add that as well. Let's do, we can do random here, maybe even, and animate the seed. I cannot. I hate this expression. Also offset to 0 and amplitude to 0.07, maybe. Let's do 32-bit float here. Let's do 32-bit float there. Also, you can see it's kind of squashed because we didn't set the resolution here properly. So it's a 640 by 480 in this noise. You can probably put down a chop somewhere to control the resolution. But yeah, so this is our noise. And let's put in something more beautiful. Let's use this. We can trim it. So 0.1 and 0.75 maybe. And yeah, this is an animation that I did some time ago. You can play with the blur how much you want. I think you don't have to overdo it here. But yeah, so blurs and noises are things you can do. You can also play with the signal in general and do some weird glitchy effects if you, I don't know, if you just mess with the resolution. I don't know which of these resolutions was like, so you can like downscale it, make it look squashed. You can add some bloom afterwards, but this is more like in the physical realm, so maybe 0.15 looks pretty nice. Wash it out a bit. How does a lens distort look here? I don't know. Yeah, I mean, that's pretty much it, I guess. Play around with the things here. You could also, if you wanted to, copy all of this and paste it out here and kind of just run the loop again. Let's see what that looks like. I haven't tried this. Oh yeah, okay. That looks messy, but it looks, I mean, you're emulating analog video here, so you can run it through multiple loops, and yeah, you can get some fun chroma banding effects here. And yeah, if you got fun ideas of how to distort the analog signal here, just leave a comment, let me know. Hope you have a great day or night. Hope to see you in the next one.